Alright, so we spent a lot of time defining formally what an integral is, and so now let's get into the semantics and the notation of integrals. So we're gonna get into integration, and so um, we said that formally the integral is defined as like the limit as n tends to infinity of this Riemann sum uh, for like all the intervals, subintervals, and subintervals, right? And this Riemann sum like implicitly is defined over like some big interval a to b, and the notation of integral, like we said that this is equal to some value I, and so this expression over here is kind of clunky, right? And so we have a different notation to represent it, and that's the notation and the semantics of integration. So this is represented by similarly by this notation, and I'm sure that this is very foreign to a lot of people, so let's get into what this whole notation is, and that is the notation of integration. So I'm going to rewrite this over here. And let's get into all the parts of it. So let's just get into this like weird S-shaped thing. This is the integral sign. And that just represents the operation of an integration. So operation of integration. So like, you know how you have the plus sign, you have an integration sign. So it tells you that we want to take the integral or find the integral of this expression. And so this f of x over here, this is known as the integrand. And so we know that how like this, we know that this like Riemann sum is or finding the exact area, because we are taking limit as n tends to infinity. We're finding the exact area of this function f, right? So the integrand is simply the function f. So if we had like a function f that looked like, you know, the normal parabola, then our integrand over here is f of x is equal to x squared. So x squared would be our integrand. Dx over here is called the variable of integration. What that means is that's the axis, I guess, that we're moving in the direction of. So I kind of motivated the integral operation as finding the area under the curve, right? But we could be finding the area under the curve like in this respect, right? But that's not what you'd be thinking about, right? So this variable of integration kind of defines what respect, like with what respect are we looking at the area, and like what axes are we kind of axes defining at. And so dx means that we're our variable that we're shifting is over like the x-axis, and so because of that we're forming like, because x is the like variable that we're shifting over, and that's our variable, we're forming our approximates or like our Riemann sums on that axis, and that helps us find the area under the curve, like anchored at the on the x-axis. And so it kind of tells us like under what axis are we finding the area under. So if it's dx, it's like this area where the axis that we're anchoring under is on x. So that's the variable of integration. The last two parts are these terms a and b, and that's the on the like the lower side of the integral. This is the lower limit of integration, and then on the upper side, this is just the upper limit. So, like I mentioned over here, implicitly in the Riemann notation, we like kind of stated that we're finding the Riemann sums on the big interval a to b, and now that is going to be explicitly stated in the integral sign, where if the if the interval that we're worried about is from some arbitrary a to b, we're going to show by writing out what the lower limit of the interval is and what the upper limit of the interval is. And that defines the range over which we're finding the area. So like if, we're worried about the interval from 1 to 5, then a would be 1 and b would be 5. So those are like all the different parts of the integral. And one thing I want to note is, let's say we had written a to b f of t dt, or we had written a to b f of u du. The idea here is all of these integrals will evaluate to the same value, even though we like kind of changed up the variable, because as long as the function itself is the same, like if the original function over here, f of x was equal to x squared, as long as when we changed the variable to u into u of u squared and then t into t squared, like we're basically doing the integral over the same function, right? We're just changing the variable name. And this is just like an important like side note, because sometimes we have like sometimes our intervals itself are variables, so we need to change up the variable in our integrand and the variable that represents the variable of integration. And because we need to change them up, it's just good to note that like even if we changed it up, it's not going to change the underlying value or like the value. And because of that, since it doesn't matter what letter we use to run from a to b, this variable of integration is sometimes called the dummy variable. And it's just like mostly just for side notes. So yeah, we have defined the notation of the integral, and so let's get more comfortable with it, and let's just do some very simple integration today. So first, we have something written in the old form, so limit as n tends to infinity, the sum from k equals 1 to n, 3 of mk squared minus 2 of mk plus 5 times delta x. Mk is midpoint of kth subinterval, and we're given that delta x is equal to 4 over n, and then our interval is from -1 to 3. And so write as an integral. And this is example 1. All right, so we know that like a lot of this information is extraneous. We don't really care how this delta is defined. We don't care what mk is, because as long as we have like some f of k or f of ck, it doesn't matter, right? What it does help us is kind of know what this what the integrand will be, right? This function, this is what our f function is, and that's what will be in our integrand. And so when we convert this, and you can just look at the definition or the conversion from the Riemann sum into an integral. What we know first is that our interval is from -1 to 3. So my lower limit is -1, upper limit is 3, and then my function that my integrand is simply gonna be 3x squared, because like mk is that variable that we're gonna pivot at in the original Riemann sum, and then minus 2x plus 5. I replaced this delta x with just a dx, right? That's my variable of integration. And that's it, right? We have represented the original Riemann sum as an integral. And notice how this is much more compact and much more simple. All right, so that was an easy starter problem. Let's get to our first sort of integral. So, and I've kind of hinted at this, but let's also like finally formally define it. So definition: if y is equal to f of x is non-negative, and integrable on the interval a to b, then the area under curve of y is equal to f of x on a to b is the integral. So essentially this is finally formally stating that the integral on some interval a to b of f of x is simply going to be the area. So whatever this value simplifies to is the area under the curve. And when we mean area, it's like the signed area. Right? This is the signed area where if we have parts of the curve that are below the x-axis and parts of the curve above the x-axis, and we're doing dx, right? This will be treated as negative area and this will be positive area. And we're not so we're not treating it as like magnitude per se, it's signed. So yeah, we have defined finally the integral as us finding the area under the curve. And so with that in mind, let us solve our second example. Evaluate this integral from -2 to 2 square root of 4 minus x squared dx. And so it might seem like we made a huge jump, right? We were just going over like some basic stuff, and now I'm just like giving you a flat integral with like equations and stuff. And we don't really have like other tools. So how do we deal with it? Well, let's go to the basic definition of the integral being the area under the curve, and let's see if this curve has some special properties, right? So we know that the square root of 4 minus x squared on that interval, well, that's the only interval where it's actually even defined, looks like a semicircle, right? And it is a semicircle. Semicircle with radius 2. And we know how to find the areas of a circle, right? And so we can easily just calculate the actual area using geometry, and that will be the value for integral. So it will simply be pi, and then r squared is 2 squared, and then divide by 2 since it's half a circle, and so we get 2 pi. And so now you've evaluated your first integral. And so sometimes you'll see like hard curves like this, and you might not even know well, later on you'll like know some integration rules, and none of the rules might seem to like match, right? But you can use some properties and the geometry of the curves in like if all else fails, like the geometry of the curve and going back to the basics can always maybe help you, right? Later on you'll learn like integrations of odd functions on some intervals also like have interesting properties. So that was our first example of an integral. And now let's do an example where we do an integration of a constant. So example 3. Integral of a constant. So specifically, let's say f of x is equal to c. We have to find the integral of c dx on the interval from a to b, right? Now I've gotten like super general, that's not even numerical anymore. So how do we go about finding a general formula for the integral of a constant over some interval? Well, like I said before, right? If all else fails, let's try to look at the geometry. We know that for constant, like if f of x is equal to c, it will be like a horizontal line, right? And let's just say we have some arbitrary a and some arbitrary b. And so we're interested in finding the area under the curve from a to b. And when we draw like the borders, we see that this is just a rectangle. And we know how to find the area for a rectangle, right? It's just width times height. So our width is b minus a, and our height is simply f of x. And f of x is always c. So now we can evaluate this, and the area is simply c times b minus a. And that is simply the area or the integral of a constant. So c dx from b to a, or a to b, is simply c times b minus a. And let's do our final basic example. Find the integral from -1 to 2 of absolute value of x minus x dx. So notice how this function is not even continuous, right? And a lot of the times when you have absolute value functions, it's much easier to deal with them if you take them on like a case by case basis, right? So yeah, I mean, so far we've been tackling these problems by looking at the graph and then dealing with geometry. So it seems like a good way to do this problem as well. So let's just take the case where x is greater than 0. This is not even defined where x is equal to 0, so we have a discontinuity there. So when x is greater than 0, this equation simply just becomes -1, right? Right, and then the case where x is less than 0, this becomes like the numerator is going to be positive, so it's going to be like some positive number, and the denominator is going to also be some positive number, so it will become 1, right? So the idea is our function will end up looking something like this. So for values greater than 0, will be a line at y is equal to -1, and then for values less than 0, we'll have a line at y is equal to 1. And the interval we're worried about is from -1 to 2. So -1, and then the area under the curve, and then up till 2, and then the area under the curve, right? And so basically what happens over here is we have a discontinuity and we have like two boxes, but that doesn't really change anything, right? If we go back to our basics, we're just finding the area under the curve. So the curve just happens to be over here, and this is the area we're worried about for x is greater than 0, and for less than 0, this is the area we're worried about. And the discontinuity shouldn't really affect us. It shouldn't affect the end of the final area because it's just like one point where we're discontinuous on. So we can take the sum, we can look at this as like two separate sums, right? We can even treat it like if the discontinuity is really worrying you, you can treat it as two separate integrals. One from -1 to 0, and then the other one from 0 to 2, right? Because that's essentially what we're doing. And so when we end up doing that, we know that this area of this box is simply 1 times 1, and then the area of this box is simply 2 times -1. And so we end up getting 1 plus -2, and so the answer is equal to -1. So in all these cases, we haven't done anything fancy. We've just relied on the geometry of the figures and the graphs, and the fact that the integral is the area under the curve. And hopefully this serves as a good introduction, and later on we'll get more into integrals and define more rules, and that will allow us to do more powerful operations.